Right. So welcome back, guys. Abdulaziz, go ahead.
دكتور في سلايدات chapter 1.9 there is a mistake actually.
Where exactly?
In the first example of height and weight.
Let me see. Let me check. Yes, for the matrix.
Yes, in the multiplication of A times A transpose.
You don't find the name, huh?
Yes, it is 20 minus 29 over 5, then minus 29 over 5, 40.
Yes, so forget about it, Abdulaziz. Work with the given matrix. Yes, better. Because their intention there is to show that well, it's not the right computational methodology to work on the variance covariance directly. So they better work on the centered matrix. That's what they say. So I checked it also in the book. They have a slightly different matrix, and it doesn't fit with the variance covariance matrix that they're given. So maybe there is a simple mistake, but there are so many ways to correct it. So I've noticed that. I said that during the lecture. Anything else, Abdulaziz?
Thank you.
Okay. So let's move forward, Shabab. So welcome back. I've sent you an announcement 2 days ago about the which announcement did I send? Sent an announcement about the YouTube channel yesterday. So I'll try to re-record the lectures. So without, because during the lectures, the kind of videos we had, if you checked it, we had not only, communication, so questions, and also I'm somehow taking your attendance. So I don't think it's appropriate to put it on YouTube like this. And so I'll try, inshallah, on behalf of Allah, I'll try to record, inshallah, and have a clean stuff, inshallah. So that's the first item. Second item, inshallah, I will post an online homework this weekend, inshallah, and you'll have like a couple of hours to do it, which includes a little bit of Python programming. So stay ready for this, inshallah. Okay? And the homework cover till section, will go till section 1.12, inshallah. Okay? Right. So I'll go forward. Yes, Abdullah.
Doctor, when will be the deadline of the homework?
Inshallah, we'll have like kind of 12 hours to do it, so we have a lot of time to do it.
Okay. Thank you.
Right. So it's not like a timed homework, like 1 hour, 30 minutes. It's a homework. Okay. Right. So let's go. Let's proceed. Skipping compared to the previously set syllabus. I've noticed that 1.11 is about norms of matrices and vectors. So there is an important part of overlapping with what we already covered, and I think it's more appropriate to move forward, since we are in shortage of time, to move directly to section 1.12, which contains maybe a little bit of more interesting material for us. Okay. So, but for your own reading, if you want to understand more deeply the norms and of vectors and matrices, you can go back to 1.11. But to me, it's not part of the syllabus anymore. Okay, so I'll go forward with 1.12, which is about factored matrices. We'll talk about tensors. Okay, so it's a short lecture actually, and I'll take time to detail some computational aspects about NMF, non-negative matrices factorization, and hopefully you'll like this. So the outline of the slides for today, we'll talk about non-negative matrix factorization. In the case of sparse principal components, and I'll talk a little bit of tensors. Okay, so if you remember, one of the most important things we've seen till now, which involves almost all the beautiful things we've studied about matrices factorization, is the concept of SVD, which is an important part of principal component analysis. So SVDs, we said, gave the perfect factors for principal component analysis until what? Until issues of sparseness. What do we mean by sparseness, Yeshiva?
Matrix full of zeros.
Yeah, so the density or sparseness issues, it means that the data matrix could be full of zeros, okay? And non-negativity, because non-negativity is it's not exactly the opposite of positive definite matrices. But we talk here about non-negativity because we are going to deal with matrices that are not possibly positive definite, but they do have entries which could be said to be all positive. So if you apply the positive definition rules, they might not work. I mean, the leading determinant, they may end up being negative. Okay, so they are not properly set positive definite matrices, but still we have to deal with them. Okay, so these are the main issues we encounter most of the time. So in many applications, for example, in portfolio optimization, in supply chain management, in vehicle routing, in many aspects, Shabab, you have to pick either 1 or 0. You buy stock or not buying the stock, and you most of the time when you buy, you also don't buy very marginal quantities. You have to buy quite important quantities because you're paying commission fees and stuff like this. So basically, let's say like your investment matrix or your decision investment matrix contains a lot of zeros because you're ignoring or overlooking a lot of stocks, and you end up having a very sparse matrix. So for many applications, these issues are quite important. And in that case, to link it with what we've seen, one might see the SVD, in fact, as a first step, but not the last step for the matrix factorization. And if you remember, we said that SVDs or generalized SVDs are quite important in, for example, in many applications, not only in machine learning and stuff like this, but also in image compression, in file compression and stuff like this. And I've seen last time the case of this black and white image compression. So today we talk mainly about non-negative matrices factorization and the special case of sparse and non-negative matrices. So this is the main dish for today, this part. Okay, so let's move forward and see what we have. So to compute what we call the NMF, NMF is for non-negative matrix factorization. We are looking for a factorization that writes A as U times V. Okay, well here U, V is supposed to be a one line row by one line column, okay? So we introduce, in fact, two vectors U and V, and we'll perform what we call alternating iterations. The concept is based on the fact that if you fix V, you try to find the right U that will minimize the distance between UV and the matrix A. And once you reach a solution for U, you fix it and you look for the corresponding V. Okay? So if you've taken already some courses on, pretty sure you guys in system engineering and electrical engineering, maybe they've taken courses in game theory or microeconomics. I'm pretty sure of that. So you know the concept of equilibrium, okay, or bargaining. So basically, it's like we are looking for a situation where once provide U to V, okay, the best V that you could provide to you is the same. Okay, so the best answer to U is V, and the best answer to V is U. Okay, we're looking for kind of equilibrium situation. You get my point, guys? In that case, we will reach a situation where the distance from A to UV is minimized, and we'll see computationally how it works. Okay, but first of all, we'd like to see what happens analytically. So we say that in this algorithm, in fact, each half step. What do we mean by half step? Yani, in a whole step, we are concerned with updating both U and V, but in half step, I'm just updating one of the vectors U or V and fixing the other. And each half step is quick because, in fact, it is effectively linear when you fix the other vector. And of course, the goal of the NMF is to approximate a non-negative matrix A greater or equal to 0. Non-negative means all the entries are positive or 0 by a low rank product UV of two non-negative matrices U and V. Okay, so for example, if you take a 2 by 2 matrix, it could be approximated by one line vector and one line column. Okay, so this idea, in fact, applies to the ordinary SVD if we include the sigmas or the singular values in the first singular values in the U. So basically, you get exactly the same stuff. So let's see first of all the proposition about the analytical solution. So what is said here is that if A is a non-negative matrix, for U and V that minimize the distance between A and UV, well, there are two cases. In fact, you'll find that U times V VT minus A VT is always larger or equal to 0. And similarly, UT times UUV minus UTA is always larger than or equal to 0. So either this is equal to 0, what is said, either the YIG is equal to 0 or the entries UIJ are equal to 0. Okay? And I will detail it on a small case. Got it, Shabab? So let me explain it on a small case with what does this mean. So I'll share with you my whiteboard here and show you what it works, how it works. So I think you prefer black, right? So let's say that matrix writes as A, B, C, D, okay? So I'm talking about a very limited case where I have a 2 by 2 matrix, and I'm looking for two vectors U with entries U1, V1, U1, U2, sorry, and the vector with entries V1, V2 that they do minimize such that I do minimize the distance between A and UV. Okay, I'm concerned with minimizing this distance. So, okay, I'd like to minimize this. So let's have a simple approach, and I'm saying like, well, let's, instead of working on the whole matrix A minus UVT, let us work on the first column you obtain. So when you do A minus UV transpose, I'm talking about this matrix, what do we obtain, Shabab? You obtain A, and here with the product, of course, I'm setting here my product UV transpose. Of course, it's going to be UV, U1, V1, U1, V2, U2, V1, and U2, V2. So don't forget, the whole U2, V2. Sorry. The whole purpose is to make this matrix work as a good approximation of our original data matrix. So if I do the subtraction, what happens? I have A, U1, V, U1, V1. I have B minus U2, V1. This is in the first column. And the second column, I'll have C minus U1, V2, and D minus U2, V2. Okay? Is it okay, guys? So let's focus on this column. I would like to minimize this column, or the magnitude of this column. What is the magnitude of this column? How can I obtain it? For column 1 here, I'll have A minus U1 V1, B minus U2 V2. So if you're looking for its magnitude, minus U2 V1, let's square it. So we avoid using the the square root. So I'll have A minus U1 V1 squared plus B minus U2 V1. And let us suppose that U is fixed, as they said in the alternating algorithm. Okay, fix U. So hopefully you understand now. Huh? So now basically, this is the norm of C1 squared, right? We're talking about. So if you differentiate the norm of C1 or the magnitude of C1 squared with respect to V1, what do you guys obtain? Of course, there is a 2 here. So you're using the chain rule basically, right? You remember? So basically, you're going to have, I'm differentiating with respect to V1. So I get minus 2 U1. So the 2 goes downstairs. And the derivative of the part inside with respect to V1 is just minus U1, right? And I get A minus U1 V1. Plus, here I'm going to have minus 2, again, U2, and multiplied by B minus U2. Of course, when I'm looking for a minimum, I'm looking first of all for a point that sets the derivative equal to 0. So what I'm interested in here is to find the right value for V1. Okay, that makes this first derivative equal to 0. So if I expand, I'm going to have the following. I have minus 2 AU1 plus 2 U1 squared V1. Am I right? Minus 2 BU2 plus 2 U2 squared V1 equal to 0. And basically, you can get easily a value for V1. You're going to have V1 equals, you can bring the 2A U1 and the 2B U2 to the side. So you get 2A U1 plus 2B U2, all divided by how much? 2 U1 squared plus 2 U2 squared. Okay? So basically, this means that to minimize when U is fixed, to minimize the magnitude of the first column in A minus UVT, you need to see V1 equal to AU1 plus BU2. You can remove the 2 as a common factor, divided by U1 squared plus U2 squared. Well, this thing, you can write it, in fact, in vector form. Okay? So it's like what? It's like the first column in A, am I right? Times U. It's AB times U. So, and downstairs, it's just UT times U. Okay? So this is the first column in U in A transpose, AB times U. Okay, any question on that, Shabab? Is that clear?
Yes,
You
clear.
hear me? Yeah, so you got it. So basically, guys, you see here you have a first a first value for V1, and by correspondence, I think you're very smart in guessing. Now, how, if the question was about, since now I have a partial solution, because I fixed U, I worked on the first column of A minus UVT, I got the perfect value for V1. Now I can use this also to get the perfect value for V2. Am I right? So I can have a guess directly. I can say that V2 also, all I have to do now is that since I'm using V2 to minimize the magnitude of the second row now of A minus UVT, second column, sorry. So basically, all what it changes is that I'm going to take from A the second column. So I'm going to have CD as a row times U over UT U. You got it? So these are the V's. In fact, I have now completely identified the V that minimizes what? That minimizes the magnitude of each one of the columns of A minus UVT. Hello? Got it? Any question on that, guys? Okay, so let's see now, record this this solution, in fact, and one can say that in general, so if you put these two together, V1 and V2 together, you can see that in fact what you just wrote is that the optimal answer sets V to be equal to AU over UTA. UTU, or A transposed, if you wish, like this, times. So this is the optimal answer we have, right? Or you can work with it also, you can write it in a kind of a different form, and you can bring the UTU to the upper side. So if you multiply both sides by UTU, you can say that, in fact, you will have UTU V minus ATU, which needs to be equal to 0. Am I right? Okay. And this part, as you see, is exactly what we had in this. This is the first condition that is written in slide. So in the slide, they said either U is 0 or you get this whole thing, the Yij equal to 0. Okay. Now, do you have any question? Because if you don't have a question, I'm going to ask a question. Beautiful. You don't have a question. Now it's my turn to ask it. Now, once V is fixed, if I set V to this value given in the first optimization of this is a half step, half iteration in my algorithm. How am I going to determine the right answer of U to this V?
Again, Doctor, can you repeat the question?
Yeah, if V is fixed, now I set V to these values, how am I going to find the right answer to this V in terms of U? And how am I going to find the right U1 and U2 that minimize, that solve the half part of the problem remaining? So, by correspondence, guys, once U is fixed, can I remove this? Yeah. I repeat, so A was equal to AB, CD. Now, if V is fixed, let's fix V. What we can do is to work on the minimization of the magnitude of each one of the rows instead of columns of A minus UVT. So I'm going to have basically, because I had UVT, which is equal to U1 V1 So we said U1, U2 times V1, V2, right? Okay. So we're going to have U1, V1 plus U2, V2. Am I right? Am I right? Right way? Let me check my notes. I'm getting confused. Yeah, I'm gonna have U1 V1. Sorry, guys. U1 V2 and U2 V1. U2 V2. So when I take A minus UV, I'm going to have A minus U1 V1, C minus U1 V2, and in this part I have B minus U2 V1 and D minus U2 V2. Okay? So now if V is fixed, I'm going to work on the minimization of the magnitude of the first row. And here I'll have the right U1 and U2. Okay? Right? And since we already have the formulas we've seen before, we can already have a guess. Previously, we said that V, the right setting for V was to write it as ATU over UTU. So by correspondence, I can see that the right setting for U would be to write it as VT A divided by the magnitude of V. Okay. We can write it like this. So this way, we can have the right setting for our problem. So as an application, a numerical application, let's do just the first step, application. Right? Let me consider that I have this beautiful matrix, which is 2 by 2, and I have 1, 2, 3, 4. Okay. And let me just start by setting, this is an arbitrary choice. Let me say that the initial U0 I'm entering with, the first iteration is set to 1, 1. Okay. So basically, I'm looking for the V vector that minimizes the magnitude of the first column of A minus UV. Am I right? So let's do the math. So we said that this should be equal to what? To AT, so 1, 2, 0. So it should be AT times U, if you wish, multiplied by UTU. Okay? How much do I find? So I'm going to have 1, 2, 3, 4, multiplying 1, 1. And what is the magnitude of 2 of U0 is going to be 1 plus 1. Am I right? So how much do I find? I find the vector V that minimizes the magnitude of the first answer to this first setting of U. So this is the half of iteration 1, in fact. How much do I find? I have 3, because I have 1 plus 2. So 3, and I have 3 plus 4, which is 7. Divided by how much? By 2. So basically, I'm saying that the right answer is to find V equals 3 over 2, 7 over 2. شايفين شباب? Okay. Hello? Yes, Firas.
How did you choose U0?
It's an arbitrary choice, as I said. The most important thing is to avoid conflictual problems, to avoid having a magnitude which is 0.
Avoid what?
To avoid having a magnitude for V,
Okay.
a norm of U equal to 0.
Okay.
Okay, so it's just an arbitrary choice. In fact, it would count. It almost have no importance when it comes to computation. It may delay the conversions just a little bit. Right. Now, once I have this V, I can use this formula also to do what? To compute the right answer to this V. So this is the first half of the iteration. So now I can write U as what? As VTA. So the V, I'm going to use the V I just found times the norm of VT. In fact. So I'm going to have what? I'm going to have 3 over 2, 7 over 2, multiplying 1, 2, 3, 4. And the magnitude here of V, of course, is going to be 9 plus 49. So 9 plus 49 over 4. 9 plus 49 over 4, yani 58 over 4. So when it comes to computation, how much do I find? I have 3. How much do I get? Maybe I wrote. Maybe I am interesting because it won't match my my answer. It should be 24 instead of 17. I think I should write it in the AVT form. It's better. AVT form is better. AV form. So let me write it AV. So I'll put here 3 over 2. Won't match. Anyways, the right answer should be 24 over 29 and 34 over 29. This is the right answer. Just give me a couple of seconds just to tell you how to get it. Yeah, basically this is it. So you have to do it like this. Let's do it just simply by AV, not AVT, just simply by AV. So you find it this way. So at this stage, we found the right answer of U to this V. Okay. Now, what I'm going to show you is how to do this computation. Now, because well, where it's beautiful to have analytical stuff, but now we understand that this is going to be a kind of a mechanical stuff, and we don't need to waste time doing this. So the beautiful thing here is that we are able now to do a little bit of programming to this. So I'm sharing with you the my programming platform, and here I'm basically let me modify the matrix a little bit. So I'm sharing with you the way I'm entering my matrix. So here it's 1, 3. We said the first row, and the second row we said I think is 2, 4. Am I right? Okay. So basically here I'm entering the matrix A. I'm initializing the 2 vectors U and V. U is initialized to 1, 1, and similarly V is initialized to 1, 1, just for computational purposes. So basically here I'm considering that U is a column and V is a row. Okay. So when I do the multiplication UV, I get a 2 by 2. Okay. Maybe we were not that careful in the analytical development, but the number match. Okay. So here I'm just writing a simple loop, guys, in Python. It looks quite similar to any other loop you can find in any programming language. So for I in the range from 1 to 10, it means that it's going to increment I going from 1 to 9, I think. So what it does here, it computes the norm of U, because, and here I'm calling the function in the LA package, in the linear algebra package, as you see. Okay, are you with me, Shabab? Are you following? And once I do this, I can just right away compute the value of the optimal answer or the optimal solution in terms of V. So V is in fact U transpose times A divided by the norm of U squared, as you see. I'm here, okay? So it's U transpose is like UTA divided by U squared, as we found in the development. I'm printing just the iteration before computing the new norm of V. So I'm computing the norm of V. Why doing this? Because I need to compute the new answer of U. So UA times V transpose divided by V squared, by the norm of V squared. Okay? And once I did this, I have completely a first approximation of our matrix A, which is, I'm calling it A0, which is just the dot product U times V. Got it? Got it, Shabab? So let's see what happens. And let me just take play with you a little bit. How many iterations do you think we need to converge towards a stable form for A, for the A0? So here I've taken like it's going to perform 10 iterations. But you will probably see that after 1 or 2 iterations, so even the values obtained by hand, they were very, very close to the values towards which we are going to converge. So it's taking a little bit of time to compile, but yeah, so let's see what we got. So Shabab, here I'm just displaying A0. So you see the A0 is kind of, let's see the last iterations, okay? You see it's kind of stable. Here is A0 is 127, 287, 1.84. So even after the first iteration, we were very close to that final value, okay? So what we can say is that this A0 is the best rank 1 approximation of our A, which was 1, 2, 3, 4, if you remember, okay? And I can even do better than this. I can even print the details of my computation. I'll print, what do I need to print? I'll print U and V, that's it. So I'll print V, first of all, and then I'll print U, just to make sure that we got the right value by hand also. So I'm expecting the first V to be about 3 over 2, 1.5, and 7 over 2. So let me go back to it. And this is it. As you see, the V we got at the beginning is 1.5, 2.5. And this answer in terms of U is the 24 over 29, 34 over 29. Okay? And first is 0, the first approximation, which acts as the best rank 1 approximation to A. Okay? And you see, just after a couple, 1 or 2 iterations, we are kind of stabilizing around value, one value of A0, which is the best rank 1 approximation to A. Do you remember something that looks like this, quite similar to this? Obtaining the best rank 1 approximation to a given data matrix. Are you still with me, Shabab? Yes, Abdulaziz.
Is it the PCA?
PCA, yes. So basically what we were doing here, with this simple iterating algorithm, we were able to find the best rank 1 approximation to our matrix. Okay? Without computing eigenvalues, without computing eigenvectors, nothing of this stuff. And I can see that even I get the application shared with you. Here I just increased the size of my non-negative matrix A, as you see. Why non-negative? Because you see all the entries are non-negative. And I'm just extended the dimensions of U and V. And I can right away obtain the size, the best rank 1 approximation without going through this SVD stuff, okay? So you see, so this is, for example, in my case, the best rank 1 approximation. What I'm interested with is to show you the values in term A0 and the approximating matrix, they kind of stabilize after a couple of iterations. Okay, so as I said in in the slides here. In fact, this converts the SVD problem to a numerical problem, okay, which is quite interesting because now we are able to find to run a couple of iterations to approximate the solution that the SVD can give me for the first and best rank 1 approximation of A. Got it? So this is where we stopped here when we left the slides. Okay, do you hear me guys now?
Yeah.
Hello? Okay,
Yes,
because I lost the connection for a couple of seconds. Right, so this is where we stopped, and this is the slide that details the work we did on this analytical problem. So for this matrix A, B, C, in fact, this problem, this beautiful problem we detailed, is in fact it summarizes the questions 1 to 5 from the problem set you have that comes with the book. Okay, so it works on the matrix A, B, C, D, and it shows that if U is fixed, you find right V with UTA over UTU, which minimizes the norms of the columns of A, and if V is fixed, U, which is equal to V times VVT, minimize the norms of rows of A. Okay, see, I made a silly mistake when I was working on the whiteboard. So hence the optimality conditions which were offered in the proposition, they are satisfied. And iteratively working, you can see that with initial setting of U, we can show that UT converges to this value and V converges to this value after 2 or 3 iterations. And in fact, we did an easy implementation for it. And in fact, the matrix we obtained A0 is the best rank 1 approximation for A. Okay? Right? Okay. Now, what we have next is the SPC. What is SPC? SPC stands for Sparse Principal Component Analysis, or Sparse Principal Component. When does this happen? It happens when you have a sparse data matrix. And we are performing here, basically, we are just exposing the main ideas behind what we will do. Okay? So, in the optimal conditions, in fact, of the NMF, there was a suggestion that the entries in U and V, they may turn to be equal to 0. So we may have a sparse approximation to our data matrix. This means that data matrix basically is going to end up to be sparse. So the idea here with the sparse vector or sparse principal components is to find the right vector Z and beta that do minimize the distance to A. So such that A is almost equal to ZB. In this situation, many algorithms have been proposed. And among the most relevant ones, you can see the lasso, which minimizes, in fact, distances from A to Z beta, plus some penalty. Here, lambda is a tuning parameter. It's a penalty on what? On the sum of the entries in the beta vector. While the elastic net method, it minimizes almost the same thing, but it adds a square term for the penalty. Okay, it minimizes also the sum of the squares of the entries in B. So it's kinds of, when you minimize this, means you are looking for a sparse vector beta when you do this. So the lasso here stands for least absolute shrinkage and selection operator. And the best beta here, since we are minimizing as part of the minimization problem, either the norms of the absolute values of the entries or the norms of the entries, will have a lot of will have, in fact, zero values, but not more than the number of components in the sample. Okay, so this is the main idea. There are some packages, if you are interested to learn more, which are available in R. This is what I've seen, or MATLAB, which can perform the lasso. Okay, and people in statistics have really more skills in doing this. So basically, we're not focusing on this part. But this is just to tell you that there are ideas behind also estimating sparse data matrices. Okay, the last part now, the last 5 minutes, I'm talking about an extension of linear algebra to D-way arrays. In fact, we talk about tensors. So for example, a 3-way tensor, if you think that a matrix is an array, so you kind of have 2 dimensions, rows and columns. So a 3-way tensor is a kind of 3D matrix. Okay? So a 3-way tensor D has elements Tij, with 3 indices. So basically, you will have a row number I, a column number J, and a column number K. So in general, a tensor is a D-way. So for example, as you've seen in the application last time, a black and white image is just a matrix of pixels. And the numbers in the matrix are grayscales that go from 0 to 156 that give the grayscale we need to color. But when we talk about the color image in fact is a 3D matrix. It's a tensor. And it has 3 slices corresponding to red, green, blue. And each slice shows the density of one of the colors, RGB. Okay? So each slice gives the density of each one of the colors. And there are many ways to represent matrices using tensors using, sorry, this is for tensors. There are many ways to represent tensors using matricized form. For example, this is a tensor supposedly. So it's supposed to be like this. It comes in a kind of cubic form. You get my point? Right? So the first phase is the first matrix, and the second phase is the second matrix. Basically, it's a way to see this data matrix in 2D instead of 3D. So this is a tensor which has how many columns, how many rows?
Two by two.
So it's 2 by 2 by 2 here, okay? It's 2 by 2 by 2. Right. Now, since we've worked on the principal components and the norms and the ranks of matrices, I'll give just a couple of ideas. So the norm of a tensor is like the Frobenius norm of a matrix. And in fact, you can consider it as, this is very easy to compute, it's just the sum of all the squares of the entries to find the norm of T squared. The rank of one tensor, the rank of a tensor is a little bit different, because rank 1 tensors are created, in fact, from products of one line, one row vectors. So if you multiply item by item the vectors A, B, C, you obtain what we call a rank 1 tensor. So in fact, a 3-way tensor could be written as just this kind of product of the 3 vectors. Okay, and here you will have indexes for I, J, and K. And the idea is to use PC or principal composition component or principal component analysis for tensors has been also developed. And we're not diving into these details, but just to tell you that they kind of use what we call CP decomposition, which tries to write a tensor as the sum of one-dimensional vector products. Okay, so it's quite similar to what we call PCA, principal component analysis for matrices. Okay, and we are not going to dive on this. This is just for your information. In fact, this looks as an extension of tensor of the SVD concept. But here the vectors A, B, and C are not supposed to be alternate to each other. And the goal is to work alternatively. You can fix 2 pairs of vectors and work on the others. Okay, all the time, like we did with the U and V in the previous case. So basically, guys, that's it for today. Thank you for following. So I end up with repeating my first announcement. So I said I will post homework, inshallah, by tomorrow. You have a number of hours, which is quite important to do it, inshallah, and submit it on the platform, inshallah. The homework will run from section almost 10.5 till section, so 1.5 till section 1.12. Okay? Any questions, Shabab? Yes, Muhammad.
دكتور بخصوص الانفايرمنت اللي نستعملها هنا بالكلاس، ممكن استعمل انفايرمنت ثانية انا مرتاح فيها اكثر او عندي تجربة سابقة معها؟
What
البايثون.
programming environment? Yes, you
Yes.
are free. Yes, of course, you are free. The most important thing is that you be able to master a little bit Python by the end of the semester.
Yes, okay, thank you.
Okay. So some students, some of your colleagues have already used Anaconda or stuff like this for their programming.